Well, good afternoon, everyone. This is Greg Schmidt with Precision Roll Grinders. I'm an application engineer here. For today's webinar, we're going to be covering the basic aspects of a design of experiment. Now, PRG always has expressed to its customers and anyone we work with that we have a team of application engineers here that is dedicated to doing design of experiments and studies at our customers to not only show to them how we can help them or how we are helping them, but to even look at some of the process variables that are having an effect on their process, and even the customer, we might not know it. So today we're just going to cover some of the very basic aspects of this. This is a very in-depth process and can take anywhere from a singular day to even weeks or more with the data analysis to get the answers that you're looking for. So the basic principles, what is a DOE? Anyone and most of the people watching this in manufacturing or other aspects, a DOE or design of experiment is looking at the correlations and the interactions of the inputs and outputs of your process. And this is used to find out which one of those, not just one, but even multiple variables, is affecting your process and your product quality. You want to use the number of factors and your factorial design, which is there on the right, to basically begin designing your experiment. Now, I'm going to jump ahead of myself here for a minute. And I'll touch on this later on, but since I have the picture here on this slide, I want to talk about it. When you're creating your design of experiment, you're going to be limited by the number of factors that you have. Whether you're looking at all the factors in your process, or in most cases, you're only looking at a couple in a specific area of your process. For example, over here, say you have 5 factors you can see on the x-axis there. To get an answer, should I say, for all 5 of those factors, you're going to have to make 32 trials or runs, which you can see there on the y-axis, where the green is full. That's basically giving you an answer for every single individual variable in that process. Now, I just want to note that it's not always necessary. As you can see, when you start getting into the higher number of factors, you have to run a lot of trials to get a full factorial design. And you don't always have to. Sometimes you can actually, for that example, I used 5 factors. Instead of doing 32 trials, you actually would do 16. And what that gives you is what they call confounding, which basically what it would say is variable A plus variable B is going to be equal to variable C plus variable D. This is not a bad thing, but when you're confronted with that situation, you have to know your process well enough to say, okay, it's A and B and not C and D, or vice versa. So if you can't confidently say that, then you probably would be looking at full factorial design. Like I said, I'm jumping way ahead of myself there, but like I said, I wanted to explain that picture, and I will touch on that later on. Now, the benefits of a DOE, obviously you have your startup benefits. In the world of manufacturing, sometimes that startup cost, when you have a annual shutdown or even an emergency shutdown, whatever it might be, when you're trying to get started back up, that is a sinkhole for money in terms of the costs. A lot of times you're not running good quality product when you first start up. There's a lot of things that are out of whack, and it ends up, like I said, becoming a very large pit for money, and it's a lot of costs. And so with a DOE, if you can optimize or understand how all the variables and your adjustments are affecting your process, you can start up that machine at the exact setting that it needs to be so it can run properly. The operator adjustments, in all manufacturing process, you've got your machine operators, and they have the ability to make these adjustments. And some of the adjustments that they're making may or may not be affecting the quality of your product. There are some adjustments that you might think are affecting your product, but are actually just interacting with another variable and by itself is not actually having an impact on it. And for that, you can make the changes more predictably. You can, write SOP or standard operating procedures for your operators to tell them, okay, are you having this defect or this quality issue? You need to change these 3 settings in this manner. So it can be really, really powerful when it comes to working with your operators and determining what those best settings are. Kind of in conjunction with that is troubleshooting. Again, when you're having those issues, you know not only what adjustments to make to fix it, but you can also know what adjustment may have caused those issues. So it's a very, very powerful tool with the information that gives you. So the whole purpose behind this is, for this example right here, your target specifications may be for that blue curve that you see in the center of this graph. And in reality, you might be running it all those different colors to the left or right, high or low, and your processes could be jumping all over the place. And the purpose of that DOE and nailing down those variables is so you can bring all those curves together around that blue one in the center there. So you're consistently running at the same specifications every time you're up and running. Now, the basic steps that are involved in a DOE is setting your objectives. So I'm self-explanatory. Why are you doing this? What aspect of the process do you want to focus on or improve or find out what variables are affecting it? So again, a lot of manufacturing process, you're dealing with very, very complex designs. And so often you want to focus on just one piece of that. Sometimes it can be very, very difficult to do your entire process, your entire machine, whatever industry you might be working in specifically. So sometimes, multiple DOEs have to be completed to, get an entire answer. So the first step is, after you set your objective, is choosing your process variables. These are also known as controllable factors. And then you also have your noise variables, or more formally, uncontrollable factors. So in a lot of processes, especially with continuous web operations, you might be looking at vibrations as a noise variable. You might be looking at speed as a controllable variable. It could be anywhere from 5 to 100 different variables you might be looking at, depending on what industry you come from. Once you've chosen your variables, then you're going to be looking at your experiment design. This is what I touched on that very first slide was choosing your factors. This is when you want to decide, okay, how many factors are you dealing with and how many trials or runs do you have to make so you're getting the answers that you are looking for. Once you've designed your experiment, you want to execute your design, which means going down that line of all those trials or runs and putting that machine or your process, whatever we might be dealing with, to those settings, and then looking at the output or results of your product. Once you've gone through all the trials and the runs, you're going to have to do a verification run. A verification run is basically the results from your design of experiment at the best settings. And so this is just going exactly what it sounds like. You're verifying that the results that your design of experiment has said to use will give you the best product. And obviously you want the verification run, you want it to be either exactly as you would expect or close, depending on the process you're dealing with. Again, when you're talking continuous web, nothing's ever perfect. You're going to have that upper spec limit and your lower spec limit, and you want to just see how if it's within that. So the analysis results this is just a couple of the large group of results that you can get from a DOE. You have your interaction plots, which you see there on the left-hand side. This is showing you how different variables are interacting with each other, or if they have an effect on each other. And basically, you see those 2 lines in the left-hand graph. The more those appear to be as an X, basically the more interaction or the more effect they're having on each other. You're going to be looking at the significance of factors, how much of an effect are the different variables individually having on your, or I shouldn't say individually, they can be together as well, but how much of an effect those variables are having. That you see in the middle there, you can see C has a very high significance or a very high effect on your process. On the right-hand side, you have a main effects plot. This is telling you individually, not interacting individually, how much those variables are affecting your process. Essentially, the more straight up and down or vertical those lines are, the more of an effect it's having on your process. For this example, fertilizer, for example, it has a very high effect. You can see spraying, because it's almost flat and not vertical, has very little effect. However, that doesn't mean you should just forget about that variable because it doesn't have effect. When you start looking at the interaction plots, a lot of times you see another factor make almost a perfect X right through, in this example, say spraying, and that even though by itself it doesn't have effect, it interacts with another variable and therefore has a large effect when it is combined with that other variable. So at the end of the day, what you want out of all of this is to shift all those curves together, or be able to shift that curve. A lot of the processes that you might be involved in or that we deal with, you're sometimes making multiple product on one machine. So the settings have to constantly change. And you want to be able to shift that curve wherever you want it, depending on your spec limits or whatever you might be looking at. And that the DOEs improve that ability to do so. You know what that machine setting needs to be at. You know how it needs to be started up. And settings might differ from startup to running conditions, but you know what they are, and so you can predictably make those changes and shift that curve to where you want it. So that is all I had for today. As always, feel free to contact us at any time. We are open 24/5 or 24/7 for emergencies. Feel free to give us a call. We can talk to you here at any of our facilities, Allentown, Carrollton, Lewisport, and Texarkana. Obviously, with COVID restrictions lifting, we have a lot more ability to travel, and we can come look at your process, talk to you about this in person. We can do it virtually, and you can come to our facility and see some of the capabilities that we have, and talk with us about these DOEs or your process. So as always, I appreciate everyone being here. If you have any questions, feel free to give us a call. And with that, I will see you next time. Thank you.